Can I start? Everyone can hear me?
Yep.
Okay, cool. So thank you very much for the invitation and for the introduction. So everything I'll talk about today is a joint work with Sean Eberhardt from Cambridge and Rudi Mrazović from San Diego. So let me start with something I think we are all familiar with, and this is Latin square. So Latin square is an n times n table filled with n symbols in such a way that each row and each column contains exactly one of each of these n symbols. And specifically, I'll be interested in transversals in Latin squares. So these are sets of n cells which are chosen in such a way that each row and each column contains exactly one of them, and no two of them contain the same symbol. So, for example, in this 5 times 5 Latin square, we have this transversal, and obviously there is no reason why there should be only one, so here's another one. But maybe the most basic question is it the case that in every Latin square there is at least one transversal? And it's actually not hard to find a counterexample. What we can do, you can just consider so-called cyclic Latin squares. And specifically, you concentrate on the ones of even order. So cyclic Latin square is a square where you first index your rows and columns with numbers from 0 to n minus 1. And then in the cell which is in column J and row I, you just put I plus J mod n. And what I claim is that for n even, this is an example of a Latin square with no transversal, and it's actually quite easy to prove that there is no transversal in such a square. So if there were a transversal, then you would have some bijection I, and so you would have, so this would be your coordinates of cells, and then modulo n, we would have the following. So this sum is this is the sum of all the entries that appeared in your n chosen cells. So this is just all the numbers from 0 to n minus 1 in some order. So when you sum this, it would be equal to n over 2 modulo n, or n even. But we know what these guys exactly are. These are just x plus 5x modulo n. And then this is equal to sum over x's and sum over x's of phi of x. But these phi of x's are again just all the numbers from 0 to n minus 1 in some order. And as we've already said, each one of these is equal to n over 2. So that means that in total, this is equal to 0 modulo n. So there cannot be such a bijection phi. Okay, so this shows you that it is possible for n even that Latin n times n square doesn't have a transversal. Obviously the question is, what about odd n's? And it's actually a very well-known open problem to prove that for n odd, every n times n Latin square has a transversal. And so this has been an open problem for more than 50 years, and I think I can safely say that we are not close to solving it. There is also a very interesting related conjecture by Rudi and Stein, which was posed 8 years later, although I think Reiser also asked basically the same question before, but for some historical reason, Rudi and Stein usually are related to this second conjecture, which says that for every n, so no matter whether n is odd or even, there is a partial transversal of order n minus 1. So partial transversal of order n minus 1 is basically the same thing. So you just need to take n minus 1 cells in distinct rows and columns, so that they all have different symbols. So obviously you wouldn't be able to have all the symbols inside them, but you still require that they are all distinct. So these two conjectures opened few different avenues of research. Maybe the one which is most relevant for us is the one where people pursued to find as large a partial consortium as possible. So like obviously the objective would be to go all the way to n-1, but like first attempts prove that you can find the partial consortium like of order n/2 and then 3/4 of n, and then at some point we achieve n minus with log of n. And in this respect, the current world record is from the last year. So it was proven by Kivash, Pokrovsky, Sudakov, and Yepreman in a very nice paper with some very nice ideas that every n times n lattice square has a partial transversal of order of n minus something a bit smaller than log n. And I can definitely recommend for you to see that paper. It has some really nice ideas. So I will actually be focused on a bit more specific problem. So I'll be focused on group multiplication tables. So for a finite group of order n, we can construct this multiplication table simply by indexing, again, rows and columns by elements of this group G, and then putting in corresponding cells such as the product of row and column this cell is in. So now one can ask, is it true that maybe in group multiplication tables one always has a transversal? But obviously the answer to this question is no. We've already actually seen the example, because Cyclic lattice square is just group multiplication table of the group Zn. And now this necessary condition that I showed you, so that we need to have that sum of all the values in your group is equal to 0, it can actually be generalized. So for any group G, we define G prime to be the usual commutator group. So for people who are not too familiar with group theory, this is just group subgroup generated by all the commutators, where commutator is basically the element of G that you get as an extra if you try to swap the order of multiplication of your elements. So let's suppose that there is a transversal in multiplication table of our group G. Well, then again, there is this bijection pi, and modulo G prime we have. Well, now again, we consider this product of all the elements that appear on the transversal. So this is just, again, all the elements in our group in some order. But then we can actually swap the order of these elements, and we will stay in the same coset of G prime. So this is just the product of the elements of our group. But then L of G is, we know that this is equal to x times pi of x, that this is the way we define our multiplication table. And then again, we can just swap the order of product of these guys. So it would be the same order of G prime, and then we get that this is just product of all the elements in our group squared. So what this means? So the order of all the elements, so the product of all the elements in our group is equal modulo G prime to that product squared. So that means that we need to have that the product of all the elements is actually in the commutator subgroup G prime. And we call this the Hall-Paige condition. So this Hall-Paige condition is a necessary condition for a group that we want to have a transversal. So there is a group theoretic characterization of this condition. So basically, this condition is equivalent to asking that the CLO2 subgroup is either trivial or non-cyclic. but basically if you don't want to worry too much about it, and you just want to think of a specific group, just take any group of odd order and that will be fine. So obviously there are also groups of even order which satisfy this, but all the groups of odd order also satisfy. Okay, so that was a conjecture by Hall-Paige, which claimed that this necessary condition is also a sufficient one. And now this is a theorem, which was finally proven more than 50 years later by Wilcox, Evans, and Bray. And I should say this proof by Wilcox, Evans, and Bray is actually a culmination of a very long series of papers. So the first steps towards the proof were done already by Hall-Paige. And then there were some series of reductions. So basically, so for example, at some point, it was proven that it is enough just to consider simple groups. And then basically how the proof was finished, it was that, that you used the classification of finite simple groups. And then you had some complete examples. And then for some of these examples, it was relatively easy to prove that the conjecture holds. And then for some others, it was much more difficult. And you actually had to use some computer algebra. But the point is the proof was very, very sophisticated and used quite difficult results from group theory. Okay. So you can actually ask even a stronger question, and that would be a question about the number of transversals in your multiplication table. So in this respect, I think there were not a lot of conjectures about what this number should be, except in the special case where G is Zn, so cyclic group of order n. And it was conjectured by Rudi and Wallace that this number of transversals should be basically 1 over e to the n times n factorial. So I think actually the story was that Rudi conjectured that this number of transversals is bounded from above by some non-trivial exponential function to the n times n factorial, and that you also have a corresponding lower bound, but these two exponential functions do not have to be the same, and then Ian conjectured that the base is actually 1 over e. So let me now try to convince you that this conjecture is actually very plausible. So you can do the following heuristic. So take Zn and odd, and then now take a random bijection from Zn to Zn, and define function psi to be the sum of identity plus your random bijection. So psi would now be just a random function from Zn to Zn. And it seems like psi should basically just be a uniform function on Zn. Like we can say that maybe on first glance there is no reason why it should favor some functions and disfavor others. So thus we get this zeroth approximation. So if psi is a uniformly distributed random function, then the probability that it would be a bijection would be n factorial over n to the n, and this would give us the number of transversals is just n factorial times that, because this n factorial is the number of ways we can choose this random bijection phi. But you can see that you can actually be a bit more careful. So the sum of all the x's when n is odd would be 0. And also the same holds for the sum of all the values of phi. So that also means that the sum of all the values of psi must also be 0. So this psi cannot just be any any function from Zn to Zn, it also must satisfy this extra property that sum of all its values is equal to 0. So in general, the sum of all of these values would be some number from Zn, so some element from Zn. So that means that actually our denominator here is not shouldn't have been n to the n. So the better estimate would be that it's actually n to the n minus 1. So so in n functions, only one of them would satisfy this problem. And you can actually do one more step. So if you take x and y from Zn to be different, and you take psi1 to be a random function which satisfies, so a random function which was used to model the distribution of psi according to these properties. So you just take a random uniform distributed function among those that satisfy this property. So then it is not hard to see that the probability that you would have this collision, so that psi1 of x is equal to psi1 of y, is just 1 over n. So if you didn't have this property, then this would be obvious, and then this extra property doesn't really change anything in the story. But let's see what is this probability when we consider the function we are actually interested in. So that would be this function psi. So the probability that psi of x is equal to psi of y, well, it is equal to this difference to be y minus x. However, this difference of phi of x and phi of y, well, we know that it cannot be equal, that it cannot be 0 because we chose phi to be a bijection. So this is actually uniformly distributed on all the elements of Zn which are not 0. And y minus x is obviously not 0 because we assume that x is not equal to y. So this means that this probability is actually 1 over n minus 1. So it's slightly more likely to have that psi of x is equal to psi of y than what our first model would suggest. So you can also phrase this in terms of expected number of collisions. So for our first model, we have that expected number of collisions is n minus 1 over 2. And for the function we are actually interested in, so the expected number of collisions is actually n over 2, so slightly larger. And now the question arises, how can we incorporate this new information we have into our model? So now we are interested in what is some sort of good model for a random function which satisfies this condition, so that sum of its values is equal to 0, and which also has this correct number of expected number of collisions. So previously, like in our zeroth approximation and our first approximation, answering this question was quite easy, and that was because so here we didn't have any condition in the zeroth approximation. We didn't have any condition for our function, so like our default choice was just let's just take uniform distributed functions. It seemed natural to have that as a default natural choice. For the first approximation, basically the same logic applied, because this was also just some condition on the support of our distribution. So we just said, well, whatever the support is, or whatever is left of the support, so set of the size n to the n minus 1, just take the uniformly distributed random function on this slightly smaller set of functions. But here, this last condition is not actually about the support of our function, so we cannot just say, well, whatever the support is, just take the distribution to be uniformly distributed. However, we can apply nice principle called principle of maximum entropy, which says that the distribution which best represents our knowledge is the one with maximum entropy. So I should say that this principle, I mean, this is just a heuristics or philosophy or whatever you want to call it, but it's certainly not mathematics. So there is no proof that this is indeed the best thing you can do, but it is a good guiding principle for heuristics. So let's define for any function f from Zn to Zn, we define this Pf to be this probability, and we also define this set H to be the set of all functions that sum to 0. So this distribution has to be supported on this set H and also have this expected number of collisions. So that means that we want to maximize entropy, which is defined this way, and the conditions are that this PFs must form a probability distribution, which has to be supported on H and also have this expected number of collisions. And you can do standard Lagrange multiplier stuff and so on, and the solution is the Gibbs distribution, which is supported on this set H, and you also now have to calculate what this vector beta is. Z of beta is just some normalizing factor of each function. Here it has to be so that Pf indeed sums to 1. Okay, so how do we choose this beta? Well, it is not hard to show that the derivative of the logarithm of this function at beta must be equal to expected number of collisions, and we know that this is n over 2. So then, if you proceed solving that, you will get that beta is basically 1 over n, and this gives you that z of beta is close to e to a half. So what this means is, let's see what happens if we take f to be a permutation, which is what we are interested in. So then, because of this condition, because n is odd, we know that sum of all the values must be equal to 0. So this then permutation would certainly be in our group, in our subgroup H. So this would just be 1. Number of collisions is for a permutation is equal to 0. So this would just be 1 over size of H times, and then Z of beta would just be e to a half. And then if we sum this over all the permutations F, we would get that the probability is n factorial over n to the n minus 1 times e to minus a half. And then the number of transversals is again just n factorial times that. So this is pretty good guess, and actually, so this is a much more precise guess than the one Wallace conjectured. So what Wallace conjectured was basically already the zeroth approximation. So, but actually, so in 2015, we proved that this second approximation is the correct one. So we proved that for n odd, the number of transversals is basically what the second approximation suggests it should be. And I should also say that, so in this paper, we phrased everything in terms of Zn, but actually it also So the same asymptotics is also true for any abelian group of odd order. So it's obviously not the case that that all the groups have all the same order, all the abelian groups of the same odd order have the same number of transversals, but the difference is only in this little of one term. So the asymptotics is the same. So for the non-abelian groups, we have basically the same thing. So we just take a group of order n which satisfies Hall-Paige condition. And again, we define this function psi in the same way as before. Zeroth approximation is the same. The first approximation is basically the same, except that now we don't claim that this product is just equal to the identity, but that this is element of the commutator subgroup. So this thing holds because of the Hall-Paige condition. So that means that we have to adjust this hypothesized count of transversals by this extra factor, so n over the size of the commutator subgroup. And again, we can do second approximation, and we will again get this e to the minus half extra factor. And last year, we proved that this second approximation is also basically correct. So we proved that the asymptotics for the transversal is basically what we also had for the abelian groups, except for this adjustment by the size of the commutator subgroup. If one is interested in proving Hall-Paige conjecture, and pretends that we don't already know that this it has been proven, one can use the result I just showed you for n large enough. So, like, obviously, whenever this little of 1 is close to 0, or so whenever it is larger than minus e to a minus half, then this whole thing would be positive, and so that would mean that you have at least one transversal. Unfortunately, this little of 1, it tends to 0, but not super fast. It's certainly faster than these rates that we got used to in analytic combinatorics, but still you have to take order of the group to be at least 10 to the 10. We can make some adjustments, so put some extra conditions on our group, so and then to lower this number 10 to the 10. But basically, what this means is that we proved the Hall-Paige conjecture for all groups which are large enough. And the important thing is that in this group we didn't use any classification of simple groups or computer algebra or anything like that. So we didn't use that for groups which are large enough. If you want to prove the whole Hall-Paige condition, then you would have to use some classification of finite simple groups to deal with these smaller groups. Also, one more result from the same paper, which is so this result is not a direct consequence of our theorem, but basically you can prove it by working a bit more to see what this little one term is, or at least what is its first approximation. And then you can prove that the number of transversals in Z2 to the K is strictly larger than the number of transversals in any other group of the same order for K sufficiently large. I'll now slowly move towards basic group idea. But before I do that, I should ask if there are any questions. Okay. The basic proof idea is to use circle method, which is a method from analytic number theory. So now I will have, I hope, like 5 minutes max crash course in circle method. So I will show you how you do it on a typical program from analytic number theory. So suppose you want to count the number of representations of your number n as a sum of 3 primes. So how can you do that? Well, you can define convolution in the usual way, and then this count that you are interested in is just the triple convolution of the indicator function of all the primes, or at least primes that you care about, so primes that are less than n, evaluated at n. You define Fourier coefficients, also in the usual way. And then some basic results from Fourier analysis give you that this count you care about is equal to this integral. So this equality is just a consequence of Fourier inversion formula. And then you can also use this very nice fact that Fourier transform of convolution is equal to the product of Fourier transforms. So this is equal to this integral. Okay. So how can you estimate this integral? Well, this Fourier coefficient would obviously be heavily dependent on what exactly this value theta is. So obviously, by triangle inequality, you can prove this upper bound, and this upper bound can actually be achieved for theta equals 0. But usually, the size of this Fourier coefficient would be much smaller than this upper bound. So usually it will be about square root of this maximum. However, there are certainly some thetas for which the size of the Fourier coefficient is pretty large. So for a third, the appropriate Fourier coefficient is equal to this sum. Now notice that these summands depend only on the residue class of M. However, M runs over primes. So there is just one prime, which is 0 modulo 3. So that wouldn't really change anything in the story. Anything significant, sorry. And then you also have these other primes, and you expect that they are basically equidistributed among the remaining 2 residue classes, so 1 and 2 mod 3. And if that is indeed the case, then it should be basically Pn over 2 times whatever is contribution for each prime, which is congruent to 1 mod 3, and then Pn over 2 times whatever is the contribution from each prime congruent to 2 mod 3. And then this is equal to minus Pn over 2. And we think of this Pn over 2 as being very large. It is constant proportion of the largest possible value. So all of these thetas for which this thing is large, you put in set M. So M would obviously have this third, and I guess you can see from this simple one here that it could also contain other rational numbers of small denominator, and it will also contain, like, from the continuity, it is obvious that it will also contain numbers which are very, very close to rational numbers with small denominator. And then everything else you put in this set called this set called minor arcs, which we denote by little n. So on this set little n, this the size of the Fourier coefficient is pretty small. And then the idea is to split this interval into two intervals. One goes over the major arcs, the other one goes over the minor arcs, and you hope that this contribution for the major arcs will be your main term, and then you hope to prove that the contribution from the minor arcs is basically just an error. So this should be a little of the main term. So this idea is actually useful in quite a lot of circumstances. So that was about it for this crash course. I hope now you know everything about simple method, and now we can move to the application in our setting. So let S be all the projections, the set of all the projections from set 1 up to n to Zn. And notice that this count we care about, so this number of transversals in Zn. So I'll just focus on the abelian case, I should say. So this number of transversals times n factorial is equal to this count. So the number of triples of projections, which satisfy that pi 1 plus pi 2 plus pi 3 is equal to 0. So why is this true? Well, like if we didn't have this n factorial, so the number of transversals, we can say that this is just equal to count of only pi 2 and pi 3 projections, such that identity plus pi 2 plus pi 3 is equal to 0. So why is that? Well, that's basically, so actually we are interested in the number of pi 2 and pi 3 such that identity plus pi 2 equals pi 3. But then we can move pi 3 to the left side because a function is a projection, if and only if minus that function is also a projection. And then we just put some symmetry. So like we multiply everything by an arbitrary, we compose everything by an arbitrary projection, and we increase this count by a factor of n factorial. So again, we define convolution. We also define Fourier coefficients. So these thetas that we've seen in this example from analytic number theory is now they are now replaced by these n tuples of elements from Zn. And then you can use Fourier analysis on Zn to n to show that this count is equal to n to the minus n times this sum of the cubes of Fourier coefficients of the indicator function of your set S. So here we did basically the same thing as before. So so these were just from the definition of convolution. And then the second equality, first we use the Fourier inversion formula of its version in this group Zn to the n. And then we also use again the same fact as before, that Fourier transform of convolution is equal to the product of Fourier transforms. Okay. So now the problem boils down to estimating this sum, and we use again a version of circle method, which would mean that we isolate the contribution of these n tuples for which the Fourier coefficient is large, and then everything else will just be an error term. So the maximum value now is n factorial. So here was the definition for transform. So f is indicator function of S. So x runs over all the elements of S. There are n factorial of them, and when all of these AIs are equal to 0, then this will just be n factorial. And there are some n-tuples for which Fourier coefficient is pretty large. So our major arcs, so those n-tuples which give you large Fourier coefficients, would be those that have almost all of the coordinates equal to some common element. So here is just a simple example of how it goes. So let's consider this n-tuple that where n minus 2 of the coordinates are equal to 0. And then you have only the first two coordinates are not equal to 0. Okay. So by definition, this is this Fourier coefficient is equal to this sum. This is equal to n minus 2 factorial times the sum over all x1 and x2, which are different and come from Zn. And then you can use the fact that sum of all the roots of unity of all nth roots of unity is equal to 0. And basically, then that will give you that this is the same as the sum of as minus sum over x1s of these guys. And now you see that if a1 plus a2 is not equal to 0, then you would have that this is just 0. And if a1 plus a2 is equal to 0, then this will just be minus n times n minus n times n minus 2 factorial. Also, I should have said here that a1 and a2 are yeah, they are not both equal to 0. Okay. Yeah, so we think of this this n times n minus 2 factorial as being quite close to this maximum value. And to show you that these Fourier coefficients can be actually much smaller than what we got here, you can consider any of the minor arcs. So minor arcs in our case would be those n-tuples that have lots of different coordinates. So we say that they have a high entropy. So for example, if you just take the most extreme case, so those n-tuples that have all, whose coordinates are all distinct, then you can see this inequality. So this equality here, this is just Parseval's inequality. So Parseval's inequality, Parseval's equality from Fourier analysis tells you that the L2 norm of your Fourier transform is equal to the L2 norm of the original function. So this is the L2 norm of your Fourier transform. The original function is indicator function of S, so its L2 norm is just n factorial. Then this n to the n, this is just some normalizing factor. But now, if all of the AIs are distinct, you can use the fact that these Fourier coefficients are independent under permutations of coordinates. So if all of the AIs are distinct, that means that in this sum, this term appears exactly n factorial times. So this will just be n factorial. So we will have n factorial times the square of this Fourier coefficient is at most n to the n times n factorial. And then this gives you that the size of the Fourier coefficient when you have all the AIs that are distinct is at most n to the n over 2, which is much smaller than the original, the maximum state. It's much more than n factorial, and also much smaller than this minus n times n minus 2 factorial, which was the value for this simple example of major R. Okay, so this was like a very rough sketch of what we did in the abelian case, and I would say even less for the non-abelian case. So in the non-abelian case, I would just say that like the basic rough idea is the same. So you still count. So you still estimate your count by some main contribution that comes from major arcs, which are defined in another way, and you also have some error coming from minor arcs, and you cannot really use abelian discrete Fourier analysis anymore. But there is a sort of variant of Fourier analysis for non-abelian finite groups, which utilizes group representations. And I think I will stop here. So thank you very much for listening.
Thank you very much for a very nice talk. Are there any questions?
Thanks, Rudi. Lovely result. I'm very excited. When your first paper came out, I asked one of your co-authors whether there was any hope of adapting to the even case, and the answer was a fairly unequivocal no at that point. Can you say anything more about how you overcame that obstacle? I guess it's just tied up in the group representations that you mentioned right at the end there.
So you mean even case in the abelian groups?
Well, I mean, so yeah, the first paper just did the odd case, and well, as I understand it, you now do everything that satisfies the Hall-Paige condition, but in particular, you do the even order abelian groups. So.
So actually, the even order abelian case it is actually handled like a year after our first paper by Sean himself. So it turned out that the difficulty in the even case is not so hard as we first thought. I think maybe it's fair to say that we didn't really, that in our original paper we were focused mostly for the cyclic groups, and for the cyclic groups in the even case you obviously have zero.
Sure.
So I think maybe if we cared a bit more in our original paper, we probably would have seen. I mean, Sean saw it a year later. So yeah.
It does seem like there's an intrinsic obstacle in the even case that just behaves differently, and even your very initial estimates. I mean, the answer is zero for some groups, but those initial heuristics don't say that.
I mean, the first one actually says that. I mean, so in the first one, this condition that n is odd is actually incorporated into this assumption for this distribution. So this condition that sum of all the values have to be zero, this is actually the fact that n is odd. But yeah, so the zeroth approximation certainly doesn't see that n is solid. So yeah, that's why it's not a perfect.
Yeah.
Yes. Yeah.
So
oh, you go, Nina.
okay, so I have a question about these minor and major arcs, because I find it surprising that you can kind of make a clear divide between major and minor arcs and say, okay, this is the main contribution, and really get both the lower and upper bound from this,
Yeah,
that it's not somehow staggered. Yeah.
That's basically because I cheated a little bit. It's not as simple as it seems from my slides. So basically, what you do is you just so for example, if you took an tuple which has like maybe, let's say it has 20 elements which are not zero, and then n minus 20 which are. Well, this would reflect on this on this, but by you will have like maybe n minus 20 factorial or something like that. So it would be significantly smaller. And then at some point you just say, well, like this seems like a major R, but its contribution is so small that we can just absorb it into the error. Yeah, there is. Yeah, the cut is not so clear as it maybe seems from my slides.
And I suppose it's the same for this example that you showed with sum of 3 primes. Can you just say major and minor, or?
I mean, no, not. I mean, that's a ternary global conjecture, and that's so Hall-Paige got proved it like 5 years ago in like. I mean, I think it's published in like 300 pages book. So yeah, I don't really know the details of how it was exactly there. So I should also say that. So I mean, if anyone here knows analytic number theory, probably the way I presented this ternary global conjecture, or like the proof of the idea of proof. Seems pretty funny, because, like, for example, number theories don't really use indicator function of primes very often. Much more popular option is to take von Neumann function, because it has some nicer, smoother properties than the indicator function. So yeah, I'm certainly not an expert.
It made perfect sense to me. I think that says how much I know about analytic number theory.
Yeah, I mean, yeah, the basic idea was just to show you that you have this integral, and then you have these large Fourier coefficients, and you have these small Fourier coefficients. And large one gives you the main term, and the other ones give you an error. Yeah, that's basically it. But obviously, I mean, the proof for ternary global conjecture is much more sophisticated. There is a reason why it is published.
Are there any other questions?
I have another one if no one else does. With your current methods, you're estimating the size of the number of transversals. Is there any hope of getting other properties of that number, such as divisors or congruences, satisfied by it? Because there do seem to be some patterns regarding this sequence, if you take it mod 8 or these sorts of things. Is there any hope of getting that kind of exact information? Obviously, you wouldn't be able to do it by just sweeping error terms under the carpet, but could some of these techniques give you something like that?
I think that would be. I think there is not much hope to improve example. So that would mean that we need to have like a perfect, almost a perfect knowledge about our minor arcs as well, because like these minor arcs then come heavily into play, and yeah, it will be really hard to calculate the exact value of minor arcs. I mean, in the end, so here, even for this, the most typical minor arc, we only bounded it from the ball. Yeah. So I think we cannot use our methods to get some divisibility properties of this kind.
In 5 years' time, you can tell me something different.
Okay. Yeah, it would be pretty cool, but I think I'm much more skeptical than we were